Okay, so hello everyone. My name is Seiji Fujimoto, currently working at UT Austin as a NASA Hubble Fellow. So today it's very my pleasure to talk about some of the exciting outcome observation results. JWST ALMA observation for the Galaxy in the epoch of ionization. But the key takeaway message from my talk today is sort of what I bring here will be one of the deepest insight of the. Oh, it doesn't work. Wait. Okay. Working. Yeah, deepest view of the early galaxy. But before going my talk, I'd like to share some of my little self-update. So I will soon move to UT, University of Toronto from next summer. And yeah, it's joining as a faculty member as assistant professor. So yeah, this is owing to the all great excitement happening in the community and also great collaboration and scientific interaction with you all. So let me keep enjoying this great moment with you all. And also another great thanks to the organizer. So this is my second time to come to this KITP workshop. The first one was almost 8 years ago. Yeah, it is always big fun to me to come here. So if any of you organize another workshop, please invite me again. Okay, let me start it. So the Kavli nicely reviewed. So one of the biggest surprise of the recent JWST discovery would be the very remarkable overabundance of the very bright galaxy, even reach beyond 10. So here is the highlight of the press release by NASA of the discovery of very bright galaxy at ratio 10, 12 from the initial JWST data. And yeah, afterwards, many multiple independent team also confirmed this high abundance from system search in the all public using all public JWST data. So the number seems to be much higher compared to the all simulation prediction made before JWST. And some systematic JWST spectroscopic work start to confirm this overabundance. So here's the UV luminosity function at ratio 12. So in spectroscopy, we cannot put every photometric candidate in the MSA design. So what we can provide here is only lower limit, but still this lower boundary start to deviate from the many simulation prediction, especially at bright end. So this remarkable overabundance start to be spectroscopically confirmed. So the next question will be, what is the physical origin of this overabundance? So as many of you know, many possible scenarios have been argued, including top-heavy initial mass function, AGN, high star formation efficiency, vast star formation, or dust-free attenuation. So to tackle this question, I think one important approach would be spatially resolved analysis for this early galaxy, because I believe this AGN or star formation activity taking place this interstellar medium scale. But in the difficulty of this kind of spatially, so the difficulty from the observation side, especially for this high latitude universe, is not only the sensitivity, but also the spatial resolution. So to overcome these two difficulties, I think one plausible idea would be maximally using the gravitation lensing effect. Then the flux boosting thanks to the lensing not only help save our observation time, but also magnification effects stretch out the structure of the galaxy. So for us, it's really easy to get down inside of the galaxy, so nailing down to the actual physics going on. And actually, we have been excited with the very great discovery of the power of JWST and lensing, some very strongly lens arc system. But this kind of very highly magnified system, too highly magnified system, this means that the magnification factor 100, 300, then this object could be too close to the cosmic line. So in this differential magnification effect, we might miss the entire galaxy, host galaxy structure. So this is very helpful to understand this specific location, but we might be missing the host galaxy property of this unique lens system. So in this context, I'd like to introduce another exciting lens system discovered at latitude 6. So this all 5 multiple images have been already identified and all are already spectroscopically confirmed. So this multiple image position, distortion, and flux ratio provides a very stringent constraint to the mass model. So we can, in general, this kind of high magnification have the large uncertainty, more than 100%. But thanks to this multiple image configuration, we have the very secure magnification estimate, less than 10% uncertainty. And another big advantage of this system is this brightest multiple images, both in fine fast side and less frame optical UV side. This object, known to the brightest object so far spectroscopically confirmed above redshift 6. So it's really helpful to have the follow-up observation, high resolution, or targeting very faint emission. But still, after lensing correction, this still representing very low mass sub-faint galaxy, very abundant population. So this is really helpful to understand what the typical picture of the early universe. And here, thanks to the great understanding of the community, here is a list of the intensive campaign for this system. So just a single lens galaxy, a total of the 100, one of the highlights here is a total of 160 hours of JWST and ALMA and MUSE time has been invested for this single lens galaxy. So that's why at the beginning of my talk, I told you that I will bring one of the deepest view of the early galaxy. And actually, thanks to the brightness of the, thanks to the great sensitivity of JWST, this beautiful near-spec IFU data obtained so the reference optical spectra. So all key emission line nicely detected just few hour exposure. And yeah, including this all key emission line information, we could achieve the best characterization of the system. And it turns out this system founding on the all main sequence relations, so the stellar mass, the formation rate, mass metallicity, or ionization, all consistent with the typical relation of the at redshift 6. So, and no evidence of the agent. So again, this is a really representative galaxy at redshift 6. But in the observed plane, it's very bright. So it provides us a very unique laboratory to understand what's going on in this early epoch of the universe. Okay, so in the next few slides, I'd like to highlight some of the exciting outcomes from this follow-up campaign. So first, the morphology. So here shows the galaxy, how one of the multiple image, how it looks like before JWST. So the HST images nicely show, yeah, so the smooth single disk-like morphology. So when we apply the cell-cycle index model, the index n equal 1 and the effective radius 0.7 kiloparsec scale, this is really typical value for this redshift and for this luminosity range. But when we look into the near-cam data, the galaxy look like this. So the single smooth disk-like galaxy resolved into at least 15 individual clumps, star-forming clumps, and after lensing correction, it's corresponding to 10 to 60 parsec scale effective radius, but accounting for the 70% of the total luminosity of the system. So this literally changing our view how the early galaxy look like. And from this morphology, we named this system like the cosmic graves. And yeah, this cosmic grave has a very nice potential or demonstrates how important the high resolution observation is. So here shows the source plane reconstructed image of the cosmic graves. So thanks to the combination of the lensing effect and also the near-cam high spatial resolution, now the effective resolution is get down to 0.01 arc-second scale. But if we don't have any lensing support, then the galaxy should be look like this. So here we apply the smoothing to downgrade the resolution to make it match to the nominal near-cam resolution 0.05. So then the galaxy look like very smooth, single disk-like object. And some of you may realize that this really looks similar to what we usually observe, even by using JWST. So here I highlight some of the high redshift galaxy candidates identified in Thales field, but actually here we can see the very similarity between two. But in reality, if we have the higher resolution, this galaxy could or might be resolved like this. Although this is n equal 1 example, but you may remember that this represents all main sequence falling on the main sequence relation, so representing very typical abundant galaxy. So this could be always the case also in the many single disk-like galaxy, even observed by recent JWST. Of course, this resolution is actually consistent with the US ELT ultimate spatial resolution. So this ultimate test will be achieved in this upcoming next generation telescope. So if you are involved with any development of this telescope, you can please use this result for the justification for the necessity of this next generation large telescope. Okay, but some of you may, if the galaxy now resolved into this numerous camps, some of you may worry that this could be just a complicated multiple merger system. So the great advantage of this system is that we also have the deep IFU data. So we can also analyze kinematics, gas kinematics, multi-phase gas kinematics from coal gas, from ALMA, and ionized gas from JWST in aspect IFU. So we find that very smooth, consistent rotating feature, both from cold and ionized gas, and here is the kinematic modeling result. So H-alpha O3C plus nicely show more or less consistent rotating feature, and velocity dispersion, somehow ionized gas have higher velocity dispersion. But this is actually consistent with simulation prediction because ionized gas is generally more sensitive to the stellar feedback. So this also confirms that C plus emission nicely traces cold underlying molecular more or less gas emission from the disk. Then by using C plus, we can also quantify, investigate instability or turbulence of this galaxy. So here shows the 2-molecule parameter equation. This is the balance between the self-gravity of the molecular gas and turbulent pressure by stellar radiation. So here, then this 2-molecule parameter generally have the threshold between 0.7 to 1, depending on the thickness of the disk. And so if the 2-molecule parameter less than this threshold boundary, then this means that self-gravity start to win. So we usually assume that, oh, this is a very unstable situation, then more disk instability happen, and clamp formation is induced. So this cosmic graph turns out to have a very low 2-molecule parameter, and also even including systematic uncertainty, falling below this threshold. So indicating that this numerous clamp would be induced by highly vigorous disk instability in the system. And actually, when we derive this 2-molecule parameter distribution, and this cyan contour is obtained from the UV clamp region, some of this UV clamp region is nicely consistent with the very low 2-molecule parameter region. So this also supports ideas that numerous clamps are induced by disk instability. So we are now resolving getting a true picture. So the early galaxies seem to be have the numerous clamp, but still embedded within smooth rotating disk. But we realize that these two features are really challenging to the current early galaxy formation evolution model. So here I highlight two simulated galaxies taken from Celer to Fire at the same redshift, similar star formation rate, similar stellar mass. Then the situation is that, okay, so the first, the panel, Celer galaxy, nicely show very smooth rotating disk, but the number of clamps is not that much. And in the Fire, it has more clamps because Fire simulation generally have more frequent burstness implemented. But subsequently, this frequent burstness produce strong feedback. Then underlying gas disks blown away. So the presence of the numerous clamp and also the smooth rotating disk are conflicting each other. To reconcile these two situations, one possible idea would be feedback effect is very weak in these early galaxies. Actually, this could be not that bad idea because high-rich galaxy getting very more compact, then the gas density getting high, then by self-shielding effect, the feedback effect can be suppressed. So this feedback effect could be very weak in the early galaxy. So we actually also verify this is really true by using the C plus luminosity as an estimate for the gas mass. So by using ALMA high resolution observation data, we also derive the spatially resolved star formation rate and gas mass density from the entire host galaxy scale to some of the individual clamp scale. So first, we find that this is more or less consistent with the local Kennicutt-Schmidt relation. But interestingly, some important thing is, some of the individual clamps start to show very high gas density, more comparable to the local ULAG scale. And if, when we look into some simulation prediction for the star formation efficiency as a function of the gas density for the molecular cloud, here I use the definition of the star formation efficiency as an integrated time average value, so the conversion efficiency to the baryon to share. Then this, actually this simulation prediction, relative hydrodynamic simulation, suggests that this level of more than 10 to 3 solar mass per parsec scale nicely suggests a very high star formation efficiency, more than 0.6 or 0.8, actually suppression of the feedback effect of the self-shielding. And actually this, some of them even meet the criteria of the feedback-free model, like Abishai's model. So this kind of strong gas density suppression of the feedback could be actually taking place. So in the introduction, I introduced several possible scenarios, but high star formation efficiency could be one of the key role playing here. But of course, some of you may remember that I also mentioned that to reproduce this numerous clump, the frequent burstness is also important. So in reality, this bursty star formation, high star formation efficiency, this combination might be taking place. And in the last slide, sorry, I'd like to also reconcile this scenario also together with some of the outflow or feedback strong scenario like dust-free model. Actually, when we take deeply into this near-spec IFU data, thanks to the high SN, we also start to capture the broad wing, so the outflow feature from the strong O3 and H alpha. But yeah, some of you also attended last week workshop discussion. Yeah, actually, Abhishek mentioned. So this, the presence of outflow does not contradict with the weak feedback. Because if the gas density is so high, the first generation stellar population, yes, supernova might happen, but this supernova feedback effect can be self-shielded from this high gas density cloud. Then this high gas density and energy only escape towards face-on direction. Then high gas density and high star formation efficiency can be maintained. So this presence of outflow does not necessarily contradict with the weak feedback or feedback-free models. Okay, so here's summary. The question is, overabundance of the very luminous galaxy, even beyond redshift 10. And now we achieved a very high resolution, very deep follow-up for the early galaxy. Now the galaxy, single disk-like galaxy, seem to be resolved into the very numerous clump embedded within the smooth rotating disk, which likely requires a bursty star formation, most likely induced by disk instability, and also a weak feedback effect. Yeah, thank you.
Thanks, Seiji. Questions, Rafa?
Thank you, Seiji. So you mentioned that you estimate the star formation efficiency as an integral over, the halo growth timescale. What about individual star formation efficiencies for the individual clumps? Do you have an idea of what would be instead the star formation efficiency per free fall time that you would estimate from the observations?
I cannot dismiss this, but let me quickly. Okay. Yeah, actually, this what I show here is okay. Okay. Yeah, what I show here is some simulation prediction of the star formation efficiency as a function of the gas density. And actually, this high gas density value is obtained from the individual clump scale. So this is actually prediction for in some of the brightest individual clumps. So not entire galaxy. So actually, in the entire galaxy, not only the due to this smoothing effect, smearing effect, the gas density looks not that high, but in the individual clumps, gas density looks very high. Yeah. So in the individual clump scale, star formation efficiency seems very high.
I'm going to take my chair's prerogative to ask a related question.
Please.
Do you have an estimate for what fraction of the mass is in the clumps compared to the diffuse component?
So the to estimate the secure stellar mass, longer wavelength filter is more important, less optical, but spatial resolution is getting low.
Yeah. So
we this clump argument, we're still using the electron UV filter, but for the electron UV, the total flux, 70% of the 70% of the total flux is coming from this individual
from
clump.
the clumps.
Yeah.
Okay.
Not for the.
Interesting. Thanks. Other questions? Yeah, Grant.
Hi. I was curious about the dynamical instabilities.
Yep.
So you showed this map of a spatial tangent cube
Yes.
parameter.
Right.
And of course that involves at the cyclical frequency, it involves the velocity dispersion, it involves sigma gas, and then of course if it's a mixture of gas and stars, it's even more complex. So you showed this band of uncertainty. Could you say a little bit more about how you measure or estimate that uncertainty and what
Right. So this Kepler value, so the frequency values, we use our best fit rotation curve. So we not assume some, just typical flat rotation. We bring the best estimate. And also, this systematic uncertainty, we think that most large uncertainty coming from the conversion factor of the gas mass. So here we use C plus emission from the tracer of this gas mass, and divided by area and sigma gas. But this conversion factor can be easily changed by factor of 2 or 3. So this shade is coming from some of the measurement uncertainty, but this bar represents the uncertainty from the conversion factor of the gas. But still including this effect, it seems falling well below this threshold.
Okay. Well, let's thank Seiji again. Thank you so much, Seiji.